We've talked about maintaining the max heap property, but we haven't talked about how we're actually going to build a heap in the first place. This figure will help us to understand how we're going to do that. Okay, so consider this array, and it doesn't have the max heap property at all. What we're going to do is we're going to go to the last node that has children, right there. And we are going to modify it as necessary so that it has the max heap property. So does that node have the max heap property? Yes, it does. So now we come to the next node back. We're going to work our way backwards. Does that have the max heap property? And the answer is no, it doesn't. And so we will swap 2 with 14. And you can see they're swapped here. So now that node has the max heap property. And we move back 1 to 3. Does it have the max heap property? No. We'll swap those two, and we see that it's max heap, the subtree is, and we come to this one, and we will swap. Now it gets a little more interesting because we are because we have a level of something greater than 1. 1 is going to have to come all the way down to here and then to here. So we're going to do a swap there and a swap there. And it turns out we already have a function that does that, and that's max heapify. So we'll call max heapify on that node, and it percolates 1 down to the bottom, and 16 kind of bubbles up to the top. And then we go to the top, it's going to get swapped with 16, then it'll get swapped with 14, and then get swapped with 8. 16, 14, 8, and then 4 is down there at the bottom. So here's the algorithm. Super simple. We will first set the heap size. Now in your programming project, you're going to want to be careful about doing that, and there's a note on that in the code. So we start at the last node that doesn't have children, which is n over 2, the floor of n over 2, and we're going to work backwards. And we simply call max heapify on each node as I showed in the example. Let's prove that it's correct. We'll do this using an invariant. So we're going to iterate, we're going to talk about this iteration there, that for loop. Before each iteration, each node j, for j is greater than I. In other words, I plus 1, I plus 2, and so on all the way to the end, I plus 2. So each node j, for j is greater than I, is the root of a max heap. So every node at index greater than I is the root of a max heap. So that's the invariant we want to show. Now let's talk about initialization of this. So I is the floor of n over 2. Now let's just reason about this looking at the picture. Now this is where we're starting, and this is our node here. Now let's look at every node after that node. So I plus 1, I plus 2, and so on. Every node j for j greater than I. Well, that's the first one. Is that the root of a max heap? Well, yeah, trivially so. It's a leaf. It has no children. Since it has no children, it has the max heap property. How about this one? also, 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 also. They're all leaves. So in this case, each node, j is greater than I, is a leaf. And thus is trivially the root of a max heap. Okay, maintenance step. Okay, by the invariant, we know that both children of I are numbered higher than I. Thus, they are roots of a max heap. So let's just look at that really quick. So let's take this one right here, the 3 there. We know that both of its children are roots of a max heap. Okay? So 9 and 10 are both, trivially so. Okay, so the children are roots of the max heap. The function max heapify assumes that both children are roots of a max heap. And the function turns node I into the root of a max heap. So if max heapify is correct, then this maintenance step is valid. And then we have termination, and it simply iterates root n over 2 times. Let's see if we can come up with a bound for the running time of build max heap. So we'll start with a loose bound. So we know that max heapify, as we've talked about before, is order log n. Now, how many times are we going to call it? Well, we start at the midpoint of the array, the floor of n over 2. And we're going to call it all the way down to 1 or 0. So we're going to call it floor of n over 2 times. Floor of n over 2 is big theta of n. We're throwing out the constant 1/2. Therefore, total time is order n log n. Right? We're calling, well, max heapify is order log n, and we're calling it theta n times. And so our total time is order n log n. It's not theta n log n because max heapify, that's only an upper bound. We don't have a lower bound on that. Okay, so that's a loose bound. Let's just reason about that for just a minute by looking at it. So how many steps are we going to have? Well, in this example, we have 1, 2, 3, 4, 5. And the total number of nodes is 8, 5, 6, 7, 8, 9, 10, and 5 is 10 divided by 2. And that's order n. Okay, so we're running it n over 2 times. And each time, let's take this example. It's going to swap approximately, in the worst case, log n times. Right? So here, we're swapping log n times. So for every node, each of these 5 nodes, we're doing log n swaps, and that gives us an n log n algorithm. Now, this bound is correct, but it's a loose bound. Can we come up with something better? And in fact, we can. And the insight is this. Let's go back to the picture. This right here, that node in that step, how many times is it going to swap? Well, we said it's going to swap at most order log n times. But really, these nodes down at the lower levels, they're swapping many fewer times, actually, than log n. The 16 and the 2 at that level, they're only going to swap at most 1 time. And so maybe it's something less than log n. Well, it turns out that we can show that the max heapify, as we had before, it's order log n, right? But it's also order h, where h is the height of that node. So if we term it that way, we can say build max heap is, and we're going to iterate over the heights. From height is 0 to the floor of log n. So we're going to iterate for each level. And at each level, we have this. Now that piece right there is the maximum number of nodes at a given height. So if we have the maximum number of nodes, so this represents the number of nodes that we're going to call max heapify on at a given level, at a given height. Then for each node, max heapify is order h. Okay, fair enough. Well, let's pull out the big O, and then we can also pull out the n because that's a constant. N for log n, h equals 0 of h over 2 to the h. Now what I did was I took that plus 1 and pulled it out. Okay, so I pulled that plus 1 out because it's a constant, because I'll just write it up here. 2h plus 1 equals 2 times 2 to the h, and so that just becomes a constant, and it comes out when we introduce the big O notation. And then the order h, the big O goes out, and we introduce everything inside the big O, and the h ends up right here. That h right there ends up here. Okay, so that's how we came up with that expression. All right, so order n now I did a couple of things here. I decided, instead of going to the floor of log n, I was going to go to infinity. Now, can I do that? Yes, because big O is an upper bound, and so I can go as big as I want. So I'm going to go to infinity, and the other thing I did was I pulled the h out and called 1 over 2h equal to 1/2 to the power of h. Okay? Now, that becomes big O of n 1/2 over 1 minus 1/2 squared. And that is by equation A dot 8 in the appendix A. So we simplified, we solved, came up with a closed form solution of the summation. And that is equal to order 2n, which is order n. Okay, now let's back up just a minute here. What does this mean? Build max heap is order n. It's linear. Every sorting algorithm we've looked at so far is at least n log n. Merge sort is n log n. But here we can get a data structure that will give us, in every case, the maximum value in the array at the root, and we can build that in linear time. It's really amazing. So in summary, we can build a max heap in linear time.